with it. Let's get started on the next section, section 11.1, where we, actually it's a new chapter, of course, where we start talking about the last huge topic of Calculus 2, which is the idea of sequences and series. Now, in everyday language, the word sequence and the word series are somewhat interchangeable. I mean, we can talk about there being a series of events. We can talk about there being a sequence of events, and they pretty much both mean the same thing. But in math, they are related, but they're not the same thing. So an example of a sequence in math would be something like this: 1, 2, 3, 4, 5, 6. Probably the world's easiest and most famous sequence, right? The natural numbers are a sequence. Okay. Here's another example: 1, 1/2, 1/4, 1/8. That was supposed to be an eighth. 1/16, and so on. That's another sequence. Notice the 3 dots on the end. What does that imply?
Continues.
You just keep on going forever. It never ends. Sequences are infinite in mathematics. They never quit. Okay. Here's another example. 2, 4, 6, 8, 10, and so on. All right. Here's another example. 1, 1/2, 1/3, 1/4, 1/5, 1/6, and so on, etc. Okay. And one more example. 1, 1, 2, 3, 5, 8, 13. Anyone care to predict the next value in this sequence?
21.
Yeah, 21. Okay. Yeah. Is everyone starting to see what's going on here?
Mm-hmm.
This is an interesting and rather famous sequence, this one. This one's referred to as the Fibonacci sequence. Fibonacci sequence. Fibonacci was an Italian mathematician. In fact, his actual name was Leonardo of Pisa, as in the Leaning Tower of Pisa, because that's the city he came from. But he used Fibonacci when he published his work. Goodness, it was like a pen name for him. You know, those were the days when mathematicians had pen names, apparently. So he came up with this sequence as a way of modeling how rabbits would breed. Now, each unit here represents one pair of breeding rabbits, and we're going from generation to generation. So at first, there's one pair of breeding rabbits. A generation later, there's still one pair because the first pair haven't managed to get their young out yet. Now there are 2 pairs of breeding rabbits. Now there are 3 pairs. Now there are 5 pairs. And how is each new term being generated here?
Add the previous number, or the previous sequence of numbers.
The previous 2 numbers, right?
Yes.
Add the previous 2. So 8 and 13 make 21. And so the next one in this sequence would be, add these 2 together. So it would be 34, etc. Okay. As I said, one of the most famous sequences that was ever created was Fibonacci's sequence. And the reason it's so famous is because, unbeknownst to Fibonacci, he didn't know this when he created it. He was just worried about modeling breeding rabbits. These numbers, these what are called Fibonacci numbers, they actually show up a lot in the real world, in natural phenomena, such as, you know, if you count this number of sunflower seeds in a sunflower seed head on the plant, in any given spiral, the number of sunflower seeds in that spiral will always be one of these Fibonacci numbers. So there may be 13 seeds in the seed head. If you count, you know, because in the seed head, you have these, like, here's the head of the sunflower plant. And then you have the seeds are organized in spirals like this out from the center. Okay. But if you were to count the seeds along a seed head, it would always be one of these Fibonacci numbers. The same kind of thing ends up happening in pineapples. If you count, you know how pineapples have lots of these kind of shapes on them, arranged. I don't know what shape are they? Are they hexagons? I don't know. But anyway, if you count those and you go all the way around the pineapple, it'll always be a Fibonacci number, that kind of thing. So Fibonacci's sequence got a lot more fame to it than Fibonacci probably thought it would ever have. But that stuff's kind of beside the point. That's not what we care about for what we're doing. We just care about it as an example of a sequence. Now, the other sequences are relatively easy to see how the next term's coming about. Here we're just counting the natural numbers. Here, what am I doing each time to get to the next one?
You're dividing by 2?
Yeah, I'm dividing by 2 constantly. Or some people might say I'm multiplying by 1/2, which amounts to the same thing as dividing by 2. Here, instead of dividing by 2, what am I doing in this next one?
Adding by 2.
I'm adding by 2, yeah. So this is called a geometric sequence, and we're going to revisit that one in a moment. This is called an arithmetic sequence. We're not going to worry too much about arithmetic sequences in this class. Turns out they're not that interesting. This one's a fairly famous sequence that we'll be coming back to later. It's referred to as the harmonic sequence. And we'll talk about why it's called that later as well. And then, of course, again, as I said, the most famous of all, the Fibonacci sequence. The deal with these sequences is, though, we need some kind of definition. We need to mathematically be precise about what is a sequence. So the book's definition is this: a sequence can be thought of as a list of numbers written in a definite order. That's one way of defining it, but it's probably not the best. So here's the definition we're going to use. Definition of what a sequence is. A sequence is a function. Now, we all know what a function is. We've been using functions for a very long time now. But what's special about these functions is all you see are the y values when you're looking at a function. These are the outputs. Y is 1, y is a half, y is a third, y is a fourth. What are the inputs if this is a function? What are my x's if these are my y's? The x's are just the numbers 1, 2, 3, 4, 5, 6, etc. So when I plug in 1, I get out 1. When I plug in 2, I get out 1/2. When x is 3, y is 1/3. When x is 4, y is 1/4, etc. Here, in example C, when x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 6, etc. So what's the domain of all of these functions that I've just listed? Sequence is a function whose domain is not just some random set of x's, but it's always the natural numbers. Okay. In some ways, you could say that our first example up at the top here, that is the domain. It is its own domain, right? Plug in 1, get out 1. Plug in 2, you get 2 as the answer. Plug in 3, you get 3 as the answer, etc. But here, in the next example, plug in 1, the output is 1/2. Plug in 2, the output is, plug in 1, the output is 1. Plug in 2, the output is 1/2. Plug in 3, the output is 1/4, etc. Okay, so a function is a sequence is a function whose domain is the natural numbers. That's important. The domain is the natural numbers. So what you can never do with these is plug in fractions for these sequences as the input. You could never plug in decimals of any kind. You only get to plug in whole numbers or counting numbers. All right, now notation for sequences. Usually we use subscripted variables when we're expressing sequences. A sequence would be thought of as being like a sub 1, a sub 2, a sub 3, a sub 4, etc. Or if you had two sequences and you want to talk about them both, you might refer to the second sequence as b. You know, like with regular functions, we talk about function f and function g. Here we're talking about sequences with a subscript and b subscript, etc. Like that. And for names of sequences, we tend to use the early part of the alphabet, A, B, C, D, as the name, as opposed to regular functions where we use F, G, and H as the names. This is just tradition. It's not a rule or anything. But when you look at your book and you look at how they're discussing sequences, they'll almost always use A with a subscript to represent a sequence, or B with a subscript to represent a sequence, etc. Or C with a subscript to represent another distinct sequence from the others. Okay, like that. All right. So what we could do is now we could come back to these examples we did up here, and we could revisit those and give them formulas using this sort of notation that we did here. So this first one, this first example we did, if we wrote it in this notation that we were just using, we could call this A sub n. And what would the formula be? You can think of n as these subscripts, like A sub 1, etc. You can think of that as being like the input. The subscript is the input, and the A sub 1 is the output. So this is kind of like saying f of 1, f of 2, f of 3, f of 4. So what is A sub n for this particular sequence? The first example up here.
N.
Exactly. It's n itself. All right. The input is 1, the output is 1. The input is 2, the output is 2. Whereas in this next example, I might call this B sub n because it's a different sequence. What's its formula?
1 over, no, wait.
Oh.
I think you were onto it. You can think of this 1 as 1 over 1, can't you?
Yes.
Is it n over 2?
It's not just the number 2 because they keep changing. So it's not always 2. If I plug in a 1, I get 1 over 1. If I plug in a 2, I get 1 over 2. If I plug in a 4, I got 1 over 2 squared. It might help you to think of the 1 here. Actually, let's do it another way. This is 2 to the power of 1. This is 2 squared. This is 2 cubed. This is 2 to the 4th, isn't it? And you can think of this 1 as 2 to the
0.
0. Does that make sense? Now can you give me a formula? It's definitely 1 over something. They're all 1 over, aren't they? But what is it? 1 over 2 to a power, isn't it?
Yes.
And that power lags 1 behind the input. So when we're inputting a 1, we get a 0 in the power. When we're on the second term, we get a power of 1. When we're on the third term, we get a power of 2. When we're on the fourth term, we get a power of 3. So when we're on the nth term, what's our power?
N-1.
Yes, n minus 1. Exactly. And so we have a formula for that sequence now. All right. Are there any questions about those so far? All right, I'm running out of space there. Because what is this next one? I think we could probably squeeze it in here. What is C sub n? If we wrote it as a formula.
2n.
Yeah, exactly. It's just 2n. It's just twice the input. When you're on 1, you get 2. When you're on 2, you get 4. On the third term, you get 6. On the fourth term, you get 8. It's just double the input that you're on. Okay, and this one? Again, you can think of this 1 as 1 over 1. This is, in actuality, D is easier than B. Because all it is what? D sub n is...
1 over n plus?
I don't think it's 1 over n plus. It's just 1 over n. Isn't that just 1 over 1, 1 over 2?
Oh, yeah.
Yeah, which is just whatever the input is, it's 1 over that. Okay. So is it making it a little clearer now, this definition? A sequence is a function. These are functions that we just wrote down, aren't they?
Mm-hmm.
Okay, but the thing is, what you'd never get to do is you'd never get to plug in for n something like pi or 1/3 or 3.9. What is the only thing we get to plug in for these n's here?
Natural numbers.
Yes, and that's why we said in this definition, a sequence is a function whose domain is the natural numbers. It's the natural numbers that you're plugging in as the input. And then the sequence values, the numbers in the list here, keep on pointing off the top of the page, I'm sorry. The numbers in this list, those are the outputs when you plug in the natural numbers. Now, this final one is the hardest of all to deal with. The Fibonacci sequence. What's E sub n, if I were to refer to that, since it's problem E, example E, I'll call it E sub n. What's its formula? Well, you can't give an explicit formula for it in terms of n. All you can do is describe it like you guys told me. It's the sum of the two previous terms, isn't it?
Yes.
So E sub n is E sub n minus 1 plus E sub n minus 2. It's the sum of the two guys that came prior to it. Okay, this is called a recursive definition. These up here are explicit formulas, but this is a recursive or implicit formula, because you can't just plug in n and get the answer. Here, if I wanted to know what's the 12th term, all I do is plug in 12 and get 1/12, right? Piece of cake, once you've got the formula. Here, if I ask you what's the 12th term, what would you have to tell me?
The 11th term and the 10th term.
Yeah, and so without knowing them, you couldn't really give the answer. So you can't tell me the 12th term without knowing the 11th and 10th. You can't tell me the 11th without knowing the 10th and 9th. You can't know the 10th without knowing the 9th and 8th. So in order to get the 12th, you'd need to know all of them, all the way back to the beginning of the sequence. This is an extremely irritating way to define a sequence, because you can't jump ahead without knowing everything that came before it. Also, you need to get this thing started, because if I don't tell you how it began, how do you know how to get the next term? You know, how do I get this first term? I have no idea. There were no terms before it. How do I get the second term? There was only one term before it, and the formula needs two terms before it. So you have to explicitly say, oh, and the first term is 1, and the second term is also 1. You need all of this information to generate the Fibonacci sequence. Does that make sense?
Mm-hmm.
So now that I've explicitly given the first and second term, now it is okay to ask what's the third term, because E sub 3 would be E sub 2 plus E sub 1, and that would be these two added together, which would be 2. So that's the third term. So you need all of that. With a recursive sequence, you need what are called initial conditions. Okay, so these are initial conditions that get things rolling. And this formula is a recursive definition. Recursion refers to the idea that you have to use old values to get new values. Those of you that have taken any computer science classes, you've probably heard about the idea of recursion in programming, where you can create new values from earlier values of the same variable. All right, so are we okay with the recursive idea?
Mm-hmm.
Okay, and then these guys here, these are all called explicit formulas for the sequence. All of these are explicit definitions. They don't use earlier values. They just use n, just plug in n and you get what you need. Okay. Any questions so far on the idea of sequences? All right. One of the most important things we need to know about a sequence is what its limit is. Even the question is, does it even have a limit? Now, what do we mean by the limit of a sequence? Well, one thing that you should fairly quickly cotton on to is you can't ask questions like this. What's the limit of this sequence as n approaches 2, for example? Because if you go back to the early days of when we talked about limits, to ask what's the limit as you approach 2, what did you have to basically do? When you very first got introduced to limits, approaching 2 meant you'd start plugging into the formula things like 1.9 and 1.99 and 1.999, and that was called the left-hand limit, wherever those answers were heading for. And then you try the other side, and again, you're approaching 2, so you try 2.1 and 2.01 and 2.001, etc. But if you think about that, that's not possible here, because what are the only things you're allowed to plug into a sequence?
Natural numbers.
Yeah, so you can't plug in 1.9 or 1.99 or 2.1 or 2.01. You can't get that close to 2. So when you ask what's the limit of the sequence, you never ask what's the limit of the sequence as n approaches some number. The only kind of limits that make sense with sequences are, what's the limit of this sequence as n approaches infinity? So unlike regular functions where you say, what's the limit of this function as x approaches such and such? With a sequence, you can just say, what's the limit of this sequence? Period. Not as x approaches anything or as n approaches anything, just what's the limit of the sequence? It's by default, it's got to mean as n approaches where?
To infinity?
Yeah, n always approaches infinity with a sequence. When you're taking the limits of a sequence, it's always the infinite limit of a sequence. There's no exception, because it's the only kind of limit that even makes sense. Now that we got that, what's the limit of this first sequence? Where is it heading towards as the n value heads towards infinity?
Infinity.
Yeah, it's pretty obviously heading to infinity. How about this second sequence, example B? Where is it heading towards as we approach infinity?
Appears to head to 0.
Yeah, it's heading towards 0. And you can actually get that from the formula too, can't you? If you put an infinity in here for n, infinity minus 1 is still infinity. 2 to the power of infinity is infinity, and 1 divided by infinity is 0. Whereas up here in our first example, if you send n to infinity, obviously, since the sequence actually with n itself, if n is going to infinity, then rather obviously n is going to infinity. Okay, how about this sequence?
Infinity.
Yeah, how about this sequence?
0.
Yeah, and we don't have a nice formula for this one. We have this recursive monstrosity here, but I think common sense tells me, where's this sequence going to go to?
Infinity.
Yeah, those are just getting bigger forever. In fact, the gaps are opening wider all the time, aren't they, between these?
Yep.
So the jump sizes keep getting bigger. It's bound to be heading to infinity, this one as well. So if we just, just in our head, without hardly doing any work, we said what the limits of these are. Okay. All right, I'm going to move on to another questions at this stage before I move on. Well, we've still got this up on the screen. All right, so before I actually write down what we just said about limits at infinity, I just want to go, because the last thing I'd written back here was about notation. I want to do a little bit more about notation, and then I'll loop back and we'll talk about limits again. But continuing on the theme of notation, we will sometimes write formulas for sequences like this: 2n over n plus 4, n equals 3 to infinity. Now, even though you've never seen this notation before, I think most of you will look at that and you'll know exactly what to do with it. If I started writing out this sequence, how would it start getting written out? What would be the first term of this sequence?
6 over 7.
Yes, it would be 6 over 7. Everyone get how that happened? Okay. It explicitly said n starts at 3. Okay, so we're disobeying what we said back here. We said a sequence is a function whose domain is the natural numbers. That really needs slight modification, or a subset of the natural numbers. Because we didn't use all the natural numbers here. We didn't start till we got to 3. Does that make sense? Okay, so normally this definition back here is what we'll use. We'll use just the natural numbers unless there's a good reason not to. Occasionally, and usually it's for convenience sake, occasionally we'll say, no, you know what, I don't want to start at 1. For whatever goofy reason here, I want to start at 3. And you can do that. You can override the general rule that you always start with 1. You just say so. I want to start at 3 instead. I want to go from 3 to infinity rather than from 1 to infinity. And the usual reason you'll change that is it might make the formula simpler. Okay. Now, if we would then carry on. So if we put in a 3, next we put in a 4, and we get 8 over 8. Then we put in a 5, and we get 10 over 9. And then we will put in a 6, and we get 12 over 10. Does that make sense?
Yep.
Okay, obviously I could reduce this one to a 1, but that's kind of beside the point right now. This would go on forever. I'd start at 3 and then just increment up towards infinity to get the terms of my sequence. So this is kind of a modified version of our original notation, where it explicitly says, oh, start at such and such a place. Okay, now sometimes they'll leave this right-hand stuff off altogether. So it'll just say this, just with the braces. Now, if it doesn't say otherwise, where are you going to start your ends at?
1.
Yeah, exactly. You'll start at 1 unless they tell you not to. Okay, if they don't want you to start at 1, they'll tell you. Otherwise, start at 1. That's the general rule with these. All right. So I just thought because I know they use this notation in the homework, and so I thought I better get that up there for you guys before we moved on to limits. All right. So now limits. Okay. Limits of sequences are always limits as n approaches infinity. There's no exception to that. They're always going to infinity when you do the limit of a sequence. Okay. So note, if such a limit exists, because remember, limits don't have to exist, right? Sometimes they exist, sometimes they don't. If a limit exists, we say the sequence converges. To that limit. Otherwise, we say it diverges. A sequence either converges or diverges, and you usually have to figure that out by using your usual limit tricks that you learned back in Math 1. Okay, so for example, find the limits of the sequences. All right, first one. Say we had a sub n is 2n over n plus 4. That's the same example as I have at the top of the paper there. What's the limit of that sequence? Well, we want to find the limit as n goes to infinity of this formula 2n over n plus 4. Now, if you put infinity in, you get infinity for the numerator, but you also get infinity for the denominator, right? So you get infinity over infinity. Now, what did we say about that back in Math 1?
Indeterminate form?
Yeah, that's indeterminate. Exactly. That's an indeterminate form. All right, so if it's an indeterminate answer of that form, infinity over infinity, what trick did you used to use back in Math 1 to find the answer?
L'Hopital's.
L'Hopital's rule, yes. Now we have a problem here in using L'Hopital's rule. L'Hopital's rule says to take the derivative of the top and the bottom.
Mm-hmm.
You cannot take the derivative of this top or this bottom. Can anybody tell me why? I mean, most of you are probably looking at that and saying, well, what's wrong with taking the derivative? The derivative, that's 2. The derivative, that's 1. What are you talking about? I can't take the derivative.
It's constant.
It's not that it's constant.
Oh,
Is it that we're not dealing with? Oh no.
Say that again. I think you maybe
Not dealing with, say, like, x in this case. Like,
it's exactly the problem. You're not dealing with x, you're dealing with n. And let's remind ourselves, what's n again?
natural numbers.
A natural number. So if you were to graph one of these functions, for example, if you were to graph this one, graphically, these have weird graphs that we're not used to. The horizontal axis is not an x-axis because we don't have an x, we have an n. Okay, and what values does n get to have?
Naturals.
Only natural values, right? And if we have the values up here, so this is the a sub n axis, not the y-axis. And if you look back up here, let's make this 2 and this 1. etc. We have the values. Let me pull this down just a little bit. 6/7, which is a little bit lower than 1, isn't it?
Yep.
Right up there. And then we have the value 8/8, which is 1 itself. And then we have the value 10/9, which is slightly bigger than 1.
Wait, we're starting at 3.
Ooh, thank you. Thanks for reminding me. Scratch this, scratch this, scratch this. So yeah, we were starting at 3. So I want to put a little dotted line here to remind me. I'm missing my whiteboard right now because I could have just marked those off with my thumb. Anyway, you know what I mean. I'm scratching those. Those values shouldn't have been there because, as you rightly pointed out, I'm supposed to start at 3. So the first value in here, when I plug in the 3, should have been 6/7. That's a little bit less than 1. Then when I plugged in 4, I literally got 1. Then when I plugged in 5, I got 10/9, which is just a tiny bit bigger than 1. And then I got 12/10. I guess that's off the screen now. 12/10 is 6/5.
Mm-hmm.
So when I plug in 6, I get 6/5, which is a little bit bigger than 10/9, but not much. But anyway, the main point here is this is not continuous, is it?
No.
And what do you know about functions that aren't continuous when you try to take their derivatives?
Cannot differentiate.
Yeah, you cannot differentiate. Exactly. You cannot differentiate. And so, no L'Hopital's rule. Unfortunately, because you cannot differentiate. That's a pain. I mean, that was our best trick. L'Hopital's rule was great. It allowed you to handle infinity over infinity with relative ease. Now we're back to not being allowed to use it again. That seems crazy. Now, I'm not done with this problem. I am going to come back to it. But I now want to visit how we can still sneak L'Hopital's rule in and use it anyway. So let me set that sheet to one side. Well, as I said, we'll come back to that example in a minute. But before we do that, let's talk about this. Let's do another graph. I'll just say consider this. This is not the graph of the function or the sequence we were just dealing with. This is just an example. And say, it doesn't really matter what the scale is here. This is just a dotted line to act as a visual guide because I don't have graph paper. Here's n, but it's also x. In other words, this axis is is got double purpose. This is a sub n, but it's also y. Okay. Now, let's just mark off our natural numbers on this axis. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say that when we plug in 1, we get this value. And then when we plug in 2, we get this value. And then 3 gives us this, and 4 gives us this, and 5 gives us this, 6 this, 7, 8, 9, 10, like that. All right. Now, looking at that sequence of dots, I think we would all conclude that this sequence has a limit. And that limit is whatever this horizontal dotted line is at, wouldn't you say?
Yes.
Those dots are approaching L. Their size is closing in on L. As I head towards infinity with my n values, these guys are approaching where the horizontal dotted line at L is. So we would say here that the limit as n approaches infinity of a sub n is L. That's graphically obvious. We don't have a formula, we're just doing this visually. Okay, now, say on top of this graph, I superimpose an actual regular continuous function that looks like this. So I'm now graphing this green graph that approaches that asymptote, doesn't it?
Mm-hmm.
Okay, so the black dots are my a sub n, and the green graph is my y. Okay? And wouldn't you say that the limit as x heads to infinity of y is also L?
Yes.
Yes.
Right? So the black dots are heading the same place as the green curve. They have the same destination. Now, this is the conclusion we're going to make. If your sequence values are lying on a curve, a joined up continuous curve, and you can find the curve's limit, and that curve's limit is L, that's the green guy, what do you have to conclude about the black dots that are sitting along that same curve? What's their limit? They're on the green curve after all.
So it would be L.
Yeah, they don't have much choice. An analogy you could make is like this. You could think of the green curve here as like a wire, and the black dots are like beads on that wire. If the wire is flattening out towards L, what do the beads on the wire have to do?
Approach the same limit.
Yeah, they're on the same piece of wire. They may have spaces between them, whereas the wire is all joined up. But even so, as you go out towards infinity, those beads on the wire don't have much choice. They're on the wire. They can't help but go to L as well. Okay? Now this leads us to a theorem. And it's a very common sense theorem. And it basically says the beads have to follow the wire. If you want to use in the language of the analogy, the beads cannot help but follow the wire. So let's say it like this. If A sub n is the same as f of n, all right, so what's that saying is the A sub n's, the black dots, have exactly the same value as the green curve at the regular natural numbers. They agree. Doesn't green and black both agree at every whole number here?
Yes.
Now, they don't agree in between because the black dots don't even exist in between. The black dots only exist at the whole numbers, whereas the green wire, it exists everywhere. But nevertheless, n here, remember, represents a natural number. So if A sub n is the same as f of n for all natural numbers n, and if the limit as x approaches infinity of f of x. Notice I've switched variables. I'm using x, not n now. In other words, I'm looking for the continuous case, the one where everything does get to have every value at once. I'm no longer restricting myself to only having whole numbers. So, and I can do that with f. I can't do that with a because it doesn't exist in between, but f exists everywhere. And if the limit of this is L, in other words, if the green wire flattens out towards L, then what can you conclude about A sub n's limit?
That it approaches L.
Yeah, it has to approach L as well. If the wire approaches L, the beads on the wire have to approach L. They don't have any choice. They're on the same wire. So what if there's gaps between them? Does that make sense to everybody? Is that logical?
Yes.
All right. Now, armed with that information, we can now revisit our question back here. We had run up against this roadblock that said, hey, when you graph this thing, it's dots. You can't take derivatives of dots. They're not continuous. How can you find a tangent line to a dot? After all, that's what a derivative gives you, isn't it? The slope of the tangent line? You can't find a tangent line at a single dot. So that's crazy. But what we're saying is, yeah, but you could join up the dots. If you join them up, and you then could find the limit of it, then the dots, the beads, have to have the same limit. So we're now going to redo our example. We're going to resume example A here. All right. So this is example A continued that I'm doing now. We had run into this. We had reached this dead end and said that the limit as n goes to infinity of 2n over n plus 4. And it had ended up being infinity over infinity. And we said, yikes, we need L'Hopital's rule, but we're not allowed to use L'Hopital's rule because they're not joined up. But according to this theorem that we just came up with right here, the limit of the sequence has to be the same as the limit of the function that is joined up. So I'm going to replace this. I'm going to trade in my n's for x's. Actually, I'm going to change this to x as well. Are you okay with that?
Mm-hmm.
So here's the wire. Sorry, here are the beads. You know, if I want to really keep on with that analogy, here are the beads, and here's the wire. All right? These are the beads up here, and this is the wire. And we're saying we can find the bead limit by finding the wire's limit. But because I've traded it in, what am I now allowed to use?
L'Hopital rule.
Exactly, I can now use L'Hopital's rule. L'Hopital's rule is now available to us because we have joined everybody up. So you do get to use L'Hopital's rule for sequences, but what you always have to do as just one step, it's not a major deal, but you always have to do what with your n's?
Swap them for x's.
Trade them in for x's and then carry on as normal with a regular old L'Hopital's rule. And it's a really easy L'Hopital's rule, this one, isn't it? All we have here is the derivative of that is 2, the derivative of that is 1, and the limit is 2, and we're done. Does that make sense?
Mhm.
Okay, so going back here on this previous graph that we just did the very start of here, these were heading uphill really quite slowly, but eventually what do they apparently do?
Approach 2.
Yeah, they eventually are approaching 2. There was not a lot of sign of that where we were. We'd only reached a value of 6/5 where we quit graphing on that original graph, but 6/5 apparently very, very slowly it's going to creep up towards 2, that sequence. All right, any questions about that example? All right, let's do another example. So example B. Let's find the limit of this sequence, B sub n.
That's true, we can't see.
Oh, I am sorry. Thanks for letting me know. B sub n is, let's let it be 1 over 2 to the n minus 1. That was one of our earlier examples, I believe, wasn't it? Something like that.
Yeah.
Yeah. In fact, that was example B, coincidentally, earlier on. All right. So what's the limit as n goes to infinity of 1 over 2 to the n minus 1? This time we don't need L'Hopital's rule. All we just do is plug in the infinity. We get 1 over 2 to the infinity. That's 1 over infinity, which is obviously 0. Does that make sense to everybody?
Yeah.
Okay. C. What if C sub n is -1 to the n plus 1? Now this becomes quite tricky. You can't plug infinity in there and make any sense out of it. Because infinity plus 1 is still infinity. -1 to the infinity power, what the heck is that supposed to be? You raise -1 to a power basically goes 2 different ways. If the power is even, you'll get 1. If the power is odd, you'll get -1.
Yeah.
So if you started to write out this sequence, it goes like this. If you put in 1, you get -1 squared, which is 1. If you put in 2, you get -1 cubed, which is -1. And then you get 1, and then you get -1, then you get 1, then you get -1. And it never quits wiggling like that, right?
Mm-hmm.
What would you say the limit of this sequence is? What's it approaching?
Does it diverge?
Yeah, it diverges. It does not approach a fixed number. It just wiggles forever. That's exactly what it does. It diverges. We say that this sequence fails to converge due to oscillation. All right, it fails to converge due to oscillation. In other words, it diverges. That's the official answer. That sequence diverges. All right, the reason it diverges is because of its oscillation. It's not approaching a fixed value. It's just jiggling all the time, up, down, and it never closes in on anything. All right, any questions about that? All right, so you don't always need L'Hopital's rule. You don't always actually even take a limit in the normal way. You sometimes just look at it and say, well, clearly that's not approaching anything. It's just jiggling forever. There's no formula here to come up with the answer. It's just common sense. All right. Are there any questions about finding limits of sequences so far?
Nope.
All right. Next topic is this. It's just a theorem about when you combine sequences with other sequences and you want to find the limits of the combined sequences. So basically, this is not what your book says, but this is what I'm going to say. The old limit rules for functions still apply. Pretty much. So, rules like this. If you take the limit of a sub n plus b sub n, so you've got two sequences, but remember, sequences are functions, remember? That was our original definition, as a sequence is a function, and the only difference is these functions have natural number domains. So these are functions. So what can you do with that limit? You can
Distribute.
Yeah, you can distribute it. And so you get the limit of a sub n plus the limit of b sub n. Okay? And it doesn't just work for plus. It works for all four operations of arithmetic. So if you were to take the limit of a sub n minus b sub n, you can again distribute. You get the limit of a sub n minus the limit of b sub n. All right? Again, with the distributing of the limit. Notice how lazy I am being with the notation. What am I not bothering to write underneath my limit?
What they're approaching.
Yeah, what it's approaching, because what is it bound to be approaching?
Infinite.
Infinity.
Yeah, it's almost not worth bothering to write down. Your book does write it down, but I will frequently leave it off when I'm talking about sequences because it's almost redundant. Of course it's going to infinity. There is no other kind of limit for sequences. If it was multiplied, still works. You can distribute it and take those two limits separately. So you get the limit of a sub n times the limit of b sub n. And division, it works as well, but with a caveat, the usual caveat. This works except when?
When the denominator is 0.
Yeah, when this lower limit is 0, unless the limit of b sub n is 0. All right. Otherwise, it's fine. You can distribute like that. Another rule from regular original limits was if there was a constant inside the limit. Notice this is not c sub n, it's just c. So that's just an ordinary constant. What can you do with that constant?
Pull it out.
Take it out.
Exactly. That still works as well. So you can pull constants out of limits of sequences. All right. And one last one here. If you take the limit of a sub n and it's raised to a power, you can actually move the limit to the inside of the power. So you can rewrite this as the limit of a sub n with a power on the outside, like that. Okay, that was a rule we had back for sequences, for regular functions as well. You can take the limit to the interior of a power, of a composite function where the outer function is a power and the inner function is whatever. You can take the limit to the inside. Okay. Now there is a restriction on this. It has to be applied only when the power is positive and the terms of the sequence are positive. Okay. You wouldn't want to be dealing with, for example, taking weird combinations of negatives in situations like that. That rule can go weird when that happens. So As long as everybody's positive, that rule does work. All right, so we've got all those, the same old rules keep working. That's the easier way to remember it.